lesson today is chapter 25 when you have paired samples or blocks. So when comparing groups that are not independent, meaning that one has an effect on the other one, then what we need to do is we need to run a paired t-test. Okay? Still dealing with means, so that's why it's a t. This usually happens when data is taken before or after an experiment. It could also be a husband and wife comparison, lots of different combinations. To work with paired data, you actually have to work with the difference of the pairs. So you're going to find out how far each pair differs, and then you're going to work with them from there. Okay? The difference of the paired groups must be independent. So the difference of one group should not affect the difference of a second group. Okay, so that's what it means by that. Okay, so when you take the mean of it, the first thing you have to do is you have to actually find the differences of all the pairs first, and then you take the mean. So be careful of that. It's the mean of the differences. And so our calculator will do most of that work for you. And then the n for this one is actually the number of pairs. So if I have 6 pairs, that's 12 different pieces of information, but again, I only count it as 6 because it's 6 pairs, okay? So for a hypothesis test, we're going to base that the difference is equal to 0, that there is no difference between the two groups, and that should be a subscript D, not a big D like that. And then based on our alternative, it can be not equal to 0, less than 0, greater than 0, depending on what we're looking for, okay? All right, so standard deviation for a paired sample, it's going to be the standard deviation. So it's the sample's deviation is what you find for the standard deviation of the difference, and so D means the difference, and I keep writing that too big, over the square root of n. And so we've used that one before, because when you do the difference, it's no longer the 2 t-test, a 2-sample t-test, it's a 1-sample because we manipulated the data to find a difference, so then that's why it's only a 1-sample, so there's only this. Okay, the margin of error, it's going to be what you found, the mean difference, plus or minus the t-score times the standard deviation, which is right here. So this goes here, which is the same thing as what we've been doing, okay? And what's fancy is the fact that we could do this on our calculator now. And so especially for the interval, this is going to be a t-interval, and that will tell you how to find it, okay? So t-interval on the calculator. Not a 2-sample, just remember it's a 1, okay? The t-score for the sample is the mean minus 0. So because, again, the difference we're going to compare was 0 over the standard error, which is right here, the standard deviation for the sample. So it's this. Okay? All right, so with our conditions, let's look at these, and we've dealt with a lot of these before. We first have to know that they're paired together. Let's try and focus, hurry up and focus, that they're paired. So it's the same person before and after. Maybe it's a husband-wife, a partner, whatever it is. It's something where you're going to compare two things, okay? And then random. There's a lot of places this can be random. It could be a random sample. It could be a random treatment. Maybe the sample's not random, but you assign groups random treatments. There's a lot of different places it can be random, okay? 10% of the population, that's the same rule, but sometimes you're going to have problems that you're not sure, so you just have to look at it. One other thing is that when between random and the population, the 10%, you can also say that you think that the sample you have is representative of the population, and so if you say something like that, that also helps clear those up, check those off. Okay, so when you look at the nearly normal, you need to make sure that you look at the differences. Are the differences nearly normal? don't really care about the L1 and the L2. You're looking at the difference. So maybe is the difference nearly normal. Okay? So what I need you to do now is let's go to the back, and I need you to go ahead and type in those numbers in L1 and L2. And when you're done, come back. Okay? All right, so now that you have them and you've read the problem, if you don't have them, really take the time to do it. So when I'm here, we are supposed to calculate the differences. The best way to do this is let the calculator do the math for you, because some of these lists are going to be long sometimes, and you're not going to want to have to do that. So go up here and highlight L3, and just type in L1 minus L2, and it's going to give you the difference. And so there's the differences. So this is the set of data that we're going to look at, okay? And so I'm going to do a 1 Vars test to get all the information on that. Make sure you're at L3, make sure there's no frequency, and we calculate. And so then there's all our numbers. So our standard deviation is 7.45. Oops, I put that in the wrong place. 7.45. Our mean is negative 5.33. And then our number is 6, which we could see that just by counting. Okay? So this negative number means that the second score was higher, an average of 5.3. Okay? Because we did June minus August. So that means that their scores went up an average of 5.3% because these are percent scores. Okay? So when we check our conditions, yes, these are paired. It's the same student before and after. Is it random? Okay. It doesn't really say whether or not it's random, but this is where we can say that we think that this is a representative sample of the kids who take the test. So representative sample of all students of the population. I definitely know that 6 kids is less than 10% of population. And then let's look at the nearly normal. So I'm going to turn on my stat plot. I had already changed it to L3 so we can graph. And that's pretty good. That's a nearly normal, okay? So the histogram looks normal. Okay, so after we've checked the conditions, now we'll run the pair test. For the conditions here, we're just going to see C above. We're not going to do it again because we already did it up there. So our hypothesis is saying that nothing happened. That means that the mean, the difference of the means is 0. There's no change. But we're trying to see if they scored better. And if they scored better, that means the August number is higher. So that means that we have a negative number because 68 minus 74 is a negative 6. So our alternative hypothesis is going to be that it's less than 0. Okay? All right, and then here the mechanics, it's based off the mean of 0. Remember that we already found our standard deviation of 7.54, and we found that our mean for that data was negative 5.33. And so we're going to see what happens. I'm not doing it real accurate, but we know it's right over here on the left. Okay, and so we're trying to find out, is that difference rare? How rare is it to get a difference of negative 5.33? So we're going to have to run a t-test. Okay? And so be careful, it's not a 2-sample t-test. We did have 2 samples, but we went ahead and found the difference of it, so it's just a 1 sample. So stat, test, t-test. I have all the numbers in here from earlier. And we want to be less than our mean, and so calculate. And so the probability of this is the p-value is 0.0698. So because there's an 8 after that 9, I would probably round it to 0.0699 or 0.07. So the p-value is 0.0699. And that's a pretty high p-value. I mean, it's not super low, but it's not super high. If it were me, I would probably fail to reject it because they're talking about running a summer school program, which costs money, right? And so with something costing that much money, 7%, that's not really good. So I would, with a p-value of 0.07, I would fail to reject. And what I would do is I would suggest that a larger sample might provide more evidence. Of whether or not the difference was good enough. Okay, so for this one, 0.07, again, that's relatively low, but if you think about it, they're talking about running summer school. And so that's, to me, that's not low enough to run a whole program to try and get improvements. Okay? All right, so